Welcome back to AI Peer Review. If you're in the thick of building or funding LLMs right now, you know the drill, right? The usual training recipe.
Oh yeah. Massive next token prediction, NTP, to start. Then you clean it up with supervised fine-tuning, SFT.
And finally, you add that last layer of polish with reinforcement learning RLHF, RLAIIF, or RLVR, as they mention in this work.
It's definitely the standard playbook.
Yeah.
But, we should always be asking, is this sequence actually the best we can do?
Right. Like reinforcement learning, its real power is that exploration, that refinement.
Exactly. So if we just tack it on at the very end, are we kind of missing a trick? Could we bake better reasoning into the base model from the get-go?
And that really sets the stage for the interesting paper we're digging into today. It's called RLP, Reinforcement as a Pre-Training Objective.
Yeah, the whole mission here is to challenge that established order, instead of RL being the final step.
The cleanup crew.
Right. They want to bring reinforcement learning pre-training much earlier, right into the foundational phase.
And the core idea, the way they do it, seems pretty clever. They treat chain of thought, COT.
That internal reasoning step models can generate.
Yeah, they treat that not just as something you want the model to output eventually, but as an exploratory action during pre-training itself.
So we're not waiting until fine-tuning to encourage reasoning. We're basically teaching the model to think for itself, much earlier on.
Okay, let's unpack that shift because it feels pretty fundamental. If you look at the standard pipeline, NTP, it's straightforward. Input goes in.
Next token comes out.
Exactly. Any reasoning is, well, it's implicit, hidden somewhere in the weights.
But RLP, it rewrites that. It introduces this explicit step where reasoning is incentivized. The pipeline is now more like input leads to a sampled COT, a thought.
Okay.
Then the next token prediction, and then crucially, a reward based on that thought. So at each step, the model samples this latent COT variable. Let's call it 0.
So the final token prediction, it's not just based on the prior context anymore.
Nope. It's conditioned on the context plus that internal thought. 2 S-days that the model just generated.
So it has to engage in what they're calling independent thinking behavior much, much earlier in the whole process.
That's the idea.
Yeah.
And think about the practical side, especially for pre-training. Normally, RL post-training needs some kind of verification.
Right. Human labels or some checker that knows the right answer. It gets expensive.
Super expensive. And slow. It needs task-specific verifiers, usually.
Right.
RLP cleverly sidesteps that. The reward signal they designed is intrinsic. It's verifier-free.
Verifier-free. How?
It's designed to work directly on just ordinary large-scale web text, stuff that isn't curated for reasoning. This basically solves the reward scarcity problem that usually keeps RL out of the early pre-training stage.
Okay, so it bridges the gap between just predicting the next token and actually getting useful reasoning later on.
Exactly. If you can generate a dense, useful reinforcement signal just from the pre-training data itself, well, that unlocks a whole new level of capability at scale.
All right, let's get into the nuts and bolts then, because this sounds like the core innovation. How do they generate this dense reward on just web text? They call it the information gain reward. What's the intuition?
The intuition is kind of like the model grading its own thoughts. It asks itself, okay, the thought I just generated, did it actually help me predict the real next token, the text, better than if I hadn't thought at all?
Okay, so if the thought was useful for prediction,
it gets a positive reward. And it's continuous, not just yes, no. If it wasn't helpful or even harmful, the reward is low or negative.
And this happens for every single token prediction, not just like at the end of a sequence.
Every single token. That's the dense part. Mathematically, the reward, it's a log likelihood ratio. You calculate 2 things for the actual observed next token, $6.
Okay.
First, $6 or a CTIA. That's the log evidence, basically the log probability of seeing $6 after generating the thought dollars.
Right.
Second, 6DIA. That's the log evidence of seeing $6 without generating any thought. That's your baseline, the no-think score.
So the reward is just the difference. You're rewarding the thought based on how much it reduced the model's surprise or cross-entropy loss for the next token compared to not thinking.
Precisely. It's the predictive utility of the thought. Did it make the next token more predictable? If yes, reward. And crucially, because this whole calculation relies only on the model's own scores and a baseline derived from itself.
That's the verifier-free part. No external judge needed.
Exactly. You could apply it anywhere on any text, web scale, code, whatever.
Okay, but what about that baseline? The SEMA, they use an EMA, an exponential moving average, teacher model. MathCal fell fee, it lags behind the main model slightly with a decay tat of 0.999. Why a moving target? Wouldn't a fixed snapshot be simpler?
That's a really sharp question. Using a moving average is actually key for stability. If you froze the baseline completely,
The main model would quickly run circles around it, and the comparison wouldn't mean much.
right, the baseline would become stale, irrelevant. But on the flip side, if the baseline tracked the main model too closely, if Tulsa is too low.
Then the difference, the reward, would just collapse towards zero. No signal.
Exactly. The lagged EMA teacher acts as this moving counterfactual. It stays relevant because it's close to the current model, but it's lagged just enough to provide a stable comparison point.
And that stops the model from just finding weird ways to get reward without actually improving. The reward hacking.
It forces the thought to genuinely improve prediction relative to a slightly delayed version of the model itself. Keeps it grounded.
Makes sense. And they back this up theoretically too, right? Proposition 1.
Yeah, that's important. Proposition 1 basically shows that maximizing this expected information gain reward is equivalent to maximizing the predictive usefulness of the thought. You're directly optimizing for the reduction in cross-entropy loss achieved by thinking. It's a well-founded objective.
Okay, so we have this neat, theoretically sound reward signal. Dense, verifier-free. But making RL stable during pre-training, that's still a challenge. How did they optimize this? Algorithm 1 gives the details.
Yeah, the optimization strategy is quite focused. They optimize an objective based only on this negative information gain loss. Lay dollar. But here's a key detail. The gradients are applied only to the parameters generating the thought tokens.
Not the parameters predicting the final token.
Well, indirectly. But the direct gradient from the RL objective only hits the thought generation policy. The reward value itself, RCTR, is treated like a fixed score during the backpropagation for that specific step.
Okay, so it isolates the learning signal to how should I think better next time?
Pretty much. And to tackle the variance, because sampling thoughts can be noisy.
They use group relative advantages. Sample multiple thoughts.
Right. Standard RL technique, but important here. They sample DR$ thoughts, usually 2 or more, for each context. Then they compute the advantage relative to the average reward within that group. It gives an unbiased estimate, but smooths things out, reduces the variance significantly, absolutely vital for stable training at scale.
All right, the moment of truth. Did all this cleverness actually result in better base models? Let's look at the QEN 3 1.7b results in Table 1.
Yeah, the results were, well, pretty striking. The RLP pre-trained model, MathCalMB, showed really significant gains. Across their 8 math and science benchmarks, RLP lifted the average score by 19% relative to the base model it started from.
19% relative, just from RLP pre-training.
Yeah. And importantly, it was also 17% relatively better than a standard continuous pre-training baseline, MathCalCPT, which just kept training with the usual next token prediction objective.
Yeah.
These are gains before any SFT or RLVR post-training.
Wow, okay. And 19% relative bump just by changing the pre-training objective. That's substantial. It suggests RLP is building a genuinely stronger foundation. But does that advantage hold up after post-training? After you apply SFT and RLVR to both the RLP model and the CPT one, does it get washed out?
That's the million-dollar question, right? And the answer is no, it doesn't wash out. This is maybe the most critical finding for anyone listening. The advantage from RLP persists and even seems to compound.
Compounds.
Yeah. After the full post-training pipeline, the RLP initialized model still came out on top, with an overall average score that was 7 to 8% higher than the conventionally trained model.
Okay, so it's not just a temporary boost during pre-training. It builds something more fundamental, more durable in terms of reasoning.
That's what the evidence suggests. And it wasn't just on this 1.7b model. They tested RLP on a much larger model too, right? The Nemotron Nano 12B V2.
Yeah, which is interesting because it's a hybrid Mamba transformer architecture. How did RLP do there? Table 2 has those results.
The results there were, frankly, staggering. RLP delivered a 35% relative improvement over the Nemotron baseline on that hybrid architecture.
35% relative gain.
35%. Let that sink in. Confirmed on a totally different modern architecture. And here's the kicker.
There's more.
They achieved this massive gain while training the RLP version on about 200 billion fewer tokens than the baseline model it was compared against.
Wait, hang on. A 35% better score, and it used 200 billion fewer tokens. That's huge. That changes the economics of training these things.
It really does. Look at the science benchmark average. It jumped by 23 points absolute. It points to RLP being a powerful lever for boosting both capability and data efficiency.
Okay, so RLP looks powerful, But how does it stack up against other attempts to put RL into pre-training? They compared it to something called RPT, reinforcement pre-training, in Table 3.
Right, that was an important comparison. And RLP came out ahead there too, showing about a 4.0% relative overall gain compared to RPT.
What's the key difference? Why did RLP perform better?
It really boils down to the reward signal's nature. RPT, as developed in earlier work, relied on sparser, often binary rewards, and it needed an extra model to kind of filter which tokens were even eligible for RL updates. It was more constrained.
Okay, less signal, less often.
It's exactly. RLP, with its dense, continuous information gain reward, applies a learning signal at every position for every token, based on its immediate predictive utility. It's just a much richer, more uniform way to guide the model towards useful internal reasoning.
And that density probably helps with versatility, too. You often hear that RL methods need really clean, curated data to work well. Did they test RLP on more diverse, messy data? Table 4 looks at different corpora.
They did, and this is a crucial point. They ran tests on different data types, academic papers, math textbooks, but also general web crawl data, just small slices, 170 million tokens each.
And RLP delivered consistent gains, around 7–9% relative improvement across all of them, even the messy web crawl data.
So it busts that myth. RLP can find and reward useful reasoning signals, even in general. Open-ended text. It doesn't need perfectly curated stuff.
Seems like it. It appears to successfully extract this transferable reasoning signal pretty broadly.
They also did a compute equivalence check, right? Also in Table 4, to make sure the gains weren't just because RLP takes more compute steps or something. Yep, a FLRP matched ablation. They took the RLP model trained on just 170 million tokens and compared it to a standard CPT baseline that was allowed to train for much longer until it had consumed 6 billion tokens, 35 times more data, but matching the compute budget.
And the RLP model, despite seeing way less data,
still came out ahead. It maintained a clear 5.3% average advantage.
Wow. Okay, so the gain really is methodological. RLP is just a more data-efficient way to instill these reasoning abilities.
That's the strong conclusion from that ablation.
All right, last practical point for listeners wanting to maybe try this. Any key hyperparameters that really mattered? Figure 2 highlights some ablations.
Two main things jumped out in their tests. First, the capacity you give the thought matters a lot. The completion length for the CUMT.
How long the internal thought can be.
Exactly. They saw big jumps going from, say, 512 to 10,024 tokens for the thought length. They found 2048 tokens was kind of the sweet spot, the best trade-off between performance gains and computational cost. So giving the model enough room to think is important.
Okay, capacity for thought is key. What else?
The other interesting finding was about regularization. Sometimes in RL, you add a KL divergence penalty, using a coefficient beta, to keep the policy from straying too far from a reference, often the base model.
Right. Keeps it stable. Did that help here?
Surprisingly, no. They found that adding this KL anchor, setting beta greater than 0, actually didn't improve performance. The optimal setting was beta equals 0, no KL penalty needed.
Huh. So the information gain reward itself provides enough structure. It doesn't need that extra leash.
It seems so. The requirement that the thought has to be predictively useful appears to be doing double duty, acting as both the learning objective and implicitly regularizing the thought process. Hashtag outro.
Okay, let's step back and pull this together. RLP, it looks like a really principled, general, and importantly, verifier-free way to build better reasoning into models right from the pre-training stage.
Yeah, by directly measuring and rewarding the predictive usefulness of the model's internal thoughts, it seems to lay down a much stronger foundation for reasoning.
And crucially, that foundation sticks around. It doesn't get washed away by later fine-tuning. It actually compounds, leading to models that are consistently better, maybe 7–8% better overall in their tests.
It really underscores how much the timing and the density of the reinforcement signal matter. Getting that useful signal in early makes a big difference.
So for you, the listener, if you're still building base models relying purely on next token prediction for the core capabilities, well, this research suggests you might be leaving significant performance and efficiency gains on the table. RLP offers a path to unlock RL's power much earlier.
And there's a fascinating detail from their supplementary results. They found RLP worked particularly well when trained on diverse data, like math and science mixed together. The different kinds of reasoning seem to actually help each other learn via this shared reward signal. Which leads to maybe a final thought to chew on. If RLP can extract this powerful reasoning signal from general web data, just by rewarding making the next token less surprising, what are the ultimate limits of using information gain or surprise reduction as the core intrinsic drive for building more complex, more general AI reasoning? especially for reasoning that goes beyond things we can easily verify. Is that simple signal enough? Something to think about.